Let's apply our newfound expanded knowledge about confidence intervals for means to this particular problem, which has the confidence interval already found for us, and we have to answer a whole bunch of questions about it. Of course, I love questions like this for exams. Just a little warning to you. So in fall of 2011, a random sample of full-time JC students was surveyed to find out the number of credit hours they were taking that semester. The confidence interval for the population mean output from StatCrunch is below. Again, StatCrunch is one of the two main computer programs that I use to work on stuff like this. Okay, so calculate the sample size. Well, the sample size isn't given to us, but they did give us the degrees of freedom. So let's write that out. So degrees of freedom is 30. That means that n must be 31, right? Because degrees of freedom is sample size minus 1. So 31 take away 1 would have been 1. Excuse me. Sorry, 31 take away 1 would have been 30. Sorry, losing my mind there just for a second. All right, so now what is the confidence level? The confidence level is 96%. It's right up at the top. You can see it right there. There, and I gave a little orange highlight so you could spot it from a mile away. All right, now we want to calculate the critical t value for that 96%. So I've already drawn the t curve, which of course you would do. So you draw your t curve, even if you're using the t table, draw it out. Then you shade it. You say, okay, I have an area in here, over here on the right, and an area over here on the left. Since my C level is 96%, 0.96, that means that alpha is 0.04, the complement of that. And that means that alpha over 2 is 0.02. All right, so then I know that it's 0.02. That would be my column if I was going to use the t-table, which you don't have to, but that's one of the ways to do it. Okay. All right, then my degrees of freedom, remember, is 30. So t, I'm looking for t 0.02 comma 30. That would be inverse t 0.98 comma 30, or you could use the t-table, either way. So let me grab the calculator. So second distribution, number 4, 0.98, 30. Go down, paste, and press enter. And I get 2.147. Okay, now let me double check that with the table if you prefer the table. So I go to the 0.02 column, I go down to 30, and there it is, 2.147, right there. Okay. So remember, for df equals 30 is the row of t-table, if that's the way you're going to do it. Again, choose, either use the table or the calculator. I don't really care which. Just use one of them. The calculator is technically the better one to use because it has all possible degrees of freedom. The table is limited to only the degrees of freedom that actually show up over here on the left-hand side. All right, now what is the standard error of the mean? Well, the standard error is given right there, 0.556776544. So let me write that out. Standard error of x bar. Remember, that's the notation for it. Or you could call it sigma x bar. Remember, we learned those notations in section 8.1. It's been a while. Is equal to, what was it again? There it is, 0.556776644. There we go. All right, so that's the standard error. Lovely. Now, we are going to calculate the standard deviation. Well, remember there's a formula for standard error. Standard error is equal to the standard deviation over the square root of n. All right, so I know that the standard error, you don't need both symbols, just pick one of them. I'll use the SE one, doesn't matter. I know that that standard error is equal to that number we just found. And I know this is equal to sigma over the square root of 31 because I found the sample size to be 31 a couple problems ago. I want to solve this for sigma. Well, it's just a little bit of a baby algebra problem. You just need to multiply both sides by the square root of 31. Now you're doing it over here because that'll cause these to divide away, to cancel for all intents and purposes. Square root of 31 over the square root of 31 goes away, and you're left with sigma over here. Okay. But you can't do it to the left-hand side without doing it to the right-hand side. Otherwise, it's not fair. So you got to multiply by the square root of 31 over here as well. So take this number and you multiply it by the square root of 31. So I'm going to grab my calculator. I'm going to need it moved over so I can see what I'm doing. Here. All right, 0.55677644 times, not that, times, there we go, the square root, so second square root 31. And I get 3.1. There you have it. Just a little bitty algebra problem. Didn't like that. So just a baby algebra problem. You just multiply both sides by your square root and you have it. Of course, you have to set it up correctly using the formula, and we learned that in section 8.1. I don't know if you remember. The central limit theorem, remember? All right, now what is the confidence interval? Well, the confidence interval is the lower and upper limit that they give us. That's the lower limit would be the left-hand part of the interval. The upper limit would be the upper hand part of the interval. So let me type that one up. There it is. I typed up those two numbers. And just for helpfulness, I circled it in a green box, and I circled the standard error in a red box, and then I went up here and circled them for you so you could see it. So standard error is the one that's circled in red, and then the confidence interval is the green one. Right, so that's the confidence interval. Now let's compute the point estimate. That would be x bar. So we're looking for x bar, which is the center of our confidence interval. Okay. All right, there I drew a little picture so you could see it here. So I have the lower side, which is 11.70462, and the upper side, which is 14.09538. And what I want is the middle of that. So I'm going to take it and I'm going to find, I got to find those numbers, 11.70462 plus 14.09538. I'm going to add them up and divide by 2. So let me grab the calculator. And you can do this a couple ways. It's easiest if you just type parentheses. 11.70462 plus 14.09538, close your parentheses, divide by 2. And you get 12.9, which is what I had written. 12.9. So you're finding the middle, you're finding the average of the two numbers, the low number and the high numbers. There's the center. That's your point estimate. Now your margin of error is the distance from the point estimate out. So you can see I kind of highlighted in pink over here. Sorry, I'm just going to make that turn into here. There we go. So it's that pink, that error, which is half the width of your interval. So you could say it's half the width of the interval. You could find the distance from the high number to the low number and divide it in 2. Or you could take the high number to that middle number you just found, that Goldilocks number, that center number. Or you could take the Goldilocks number, 12.9, and subtract away 11.7. One way or another, you have to find that distance from the edges to the center. All right, there we go. I typed up the first one. So that's like it's half the width of the interval. Sorry. So the width of the interval is the distance from the high number to the low number. Not that one, this part. All right, so I want to take high number, which is 14.09538. I'm going to subtract away 11.70462. Then I'm going to divide that in half. And I get 1.19538. Awesome. Cool. All right, so I could do it with the calculator taking the high number, which is 14.09538, and subtracting away my Goldilocks number in the middle, my mean, which is 12.9. Or I could take 12.9, take away 11.70462. That would also work. Every way I do it, I get 1.19538. There we go, I wrote it up that way. So you could take 14.09538, take away the mean of 12.9, the center, sample mean, or you could take 12.9 and subtract away 11.70462. Any which way you do it, you're going to get 1.19538. And we are all done with section 9.2. I'll see you back here for 9.3 when we'll learn about the chi-square distribution. See you then.